why or how the universe got into the state that we call the Big Bang. So we don't know whether the universe existed before that. We have theories that it did. Theories called inflation, which are very popular theories. You'll find them in all the textbooks, which say that before the universe was hot and dense, which we used to call the Big Bang, space and time is still there and the universe is expanding extremely fast, which it's called inflation. And then that period draws to a close and that expansion sort of slows down and almost collapses and changes, and the energy that was driving the expansion gets sort of dumped into space and changes, and ultimately makes the particles out of which we are made. So that's actually the standard model of cosmology now. So we do have an idea that we redefine the Big Bang as the hot Big Bang, and it's not the origin of the universe in time, it's the end of inflation. And then you get the question, what is inflation there? What did that have a beginning? And the answer is that in Einstein's theory alone, then yes, and Roger Penrose actually, and Stephen Hawking proved this a long time ago, that just given Einstein's theory you have this singularity, just like kind of like the black hole singularity, but at the beginning of time. But we do know that when you put quantum mechanics in and add that in, then it gets messy and we don't really know what that means. And so Stephen Hawking had a thing called the no boundary proposal, all sorts. Basically the point is we don't know. So we don't know whether the universe had a beginning in time, I would say is the correct statement as we are at the moment. It's part of the reason why, by the way, getting back to the black holes, they're important and interesting, because the study of black holes and this idea of information and how does it get out, that's leading us to suspect that space and time themselves are not fundamental, but they emerge from something else. So just in the way that we've been talking about consciousness emerging from this physical structure in our heads. So we don't know how it emerges. It's a very strange thing, but it emerges from this collection of atoms right in a particular pattern. Well, we think now from the study of black holes that space and time emerge from something else, which is kind of one way to describe it, is just a quantum theory. So it's in quantum computing terms, it would be just qubits. So a network of qubits entangled together just like a quantum computer. Out of that, we suspect that space and time might emerge. So surely we have to understand that process, and we don't really fully understand that, but we have glimpses of it in much more detail to start talking about the origin of time, because in order to talk about the origin of time, you have to know what it is, and we don't actually know what it is, which is, and that's kind of when you say that it sounds bizarre, doesn't it? How can you not know what time is? I think Einstein once said that it is the thing that you measure on a watch, but he said that as kind of almost a joke, because you assume in Einstein's theory there's a thing that the watch measures, but what actually it is at the deepest level is a good question. So, but it's funny, it's interesting that study of black holes is forcing us towards these theories. It's not that we had the theories space and time emerging from something and found and decided we could check it by thinking about black holes. It's come the other way around, really. So it's interesting, but that almost makes the universe look in some ways like a giant quantum computer, which is not to say that we live in a simulation before you ask, but it just looks like there's a description of the universe that looks like a quantum computer type description that doesn't have the concept of space or time in it. I think everybody does. I think every scientist that no scientist can picture that number. I mean, even the small number 200 billion, which is the number of stars in one galaxy, and then when you say 2 trillion galaxies, that's, I challenge anyone to be able to picture that, but it is the reality that we've observed. We haven't counted all 2 trillion, by the way. We have a thing called the Sloan Digital Sky Survey, which maps the positions of galaxies, so you can, how much of the sky you've surveyed and how many GYs you've counted, and then you can spread that across the wider universe and you get this picture of a vast and possibly infinite universe. We know that the universe, I very strongly suspect that the universe is much bigger than the piece we can see. So we have good reason to think that's the case. Whether it's infinite or not is another question. And then that goes to your, that can you picture infinity? Well, no one can picture infinity. There's a weird thing as well about, we say the universe began 13.8 billion years ago. So that's a measurement because we can measure the speed that all the galaxies are flying away from us, essentially, and then you can run time backwards if you like to find out when they were all on top of each other, and so it's quite a simple measurement, and we've done that. So we say the universe began 13.88 billion years ago, but actually all we know really was the universe was very hot and very dense at that time. And we have some theories that the universe was in existence before that, and perhaps some sort of circumstantial evidence, and that means that actually the universe could have always been there, eternal, And when I talk to people, sometimes some people get upset about that. Some people would rather it had a beginning. And the idea that it might have been around forever is more frightening somehow than the fact that it began. It's interesting the way that people's minds work. What terrifies you the most? An eternal universe or a finite universe? Those theories are back in vogue. Some of those theories are back in vogue again. So yes, some of them say that there's a cycling universe. So the Big Bang is an event when space gets very hot and very dense and filled with particles, and that may happen again, or some of the other theories. There's a theory called eternal inflation, which is a theory that, and it's actually the most popular theory I think at the moment for what happened, but why the Big Bang is the way that it is. But it's got some very special features, the Big Bang, which we could talk about. But inflation is the idea that space-time was around before the Big Bang, and it was expanding extremely fast. There was doubling in size in the most popular of these theories every 10^37 seconds, which is 00 with 37 knots 1 of a second. So it's an unimaginably fast expansion. And then the idea is that draws to a close, so it quite naturally sort of dies away, and the expansion slows down, and all the energy that was taken that was causing that expansion sort of gets dumped into space and heats it up and makes particles, and that's what we call the Big Bang. And those theories that the slight extension to those say that slowing down just happens in little patches. So most of the universe, the overwhelming majority of the universe, is still inflating at that insane sort of speed, and the just little patches stop and they're big bangs. So you get multiple universes, a multiverse. It's called the inflationary multiverse, and we are in one of those bubbles. And that's one of the more popular theories. Enrico Fermi is one of the great physicists, legendary Italian physicists who laid many of the foundations of modern 20th century physics, so-called Fermi direct statistics and all sorts of things. If you do a degree in physics, then you will spend a lot of time revising equations and theories that Fermi did. One of the great legends, the Fermi Paradox, is it's probably the thing he spent least time on actually, is almost one throwaway remark that he delivered. And the question is, where are they? By they I mean aliens. The heart of the Fermi Paradox is this. We know that we live in a big old galaxy in a big old universe, and let's for the purposes of this discussion confine ourselves to the Milky Way galaxy. The Milky Way galaxy we now know has something like 400 billion suns. And we now know that most of those suns have planetary systems around them, so trillions of planets. The galaxy's been around for pretty much the age of the universe, 10 billion years plus. And so there's a lot of real estate, and there's been plenty of time for civilizations to develop in the galaxy. The Fermionic paradox at its heart is the statement that, notwithstanding the fact that there have been billions of years on billions of worlds for civilizations to arise, we see no evidence of any of them in the galaxy at all. So the paradox is why? It's a paradox, and I think it's a very good question. It's an extremely good question, and there can be many answers, and the great fun, or I would say the intellectual value of the Fermi paradox, if we accept that we haven't seen any. So let's accept that. Let's accept that there isn't a UFO sat in some warehouse in Roswell or something like that. Let's accept that we haven't seen any. Let's accept, well, we have to accept the picture that I've just given you about the Milky Way galaxy and its age, because that's a measurement. So we know that. The question is then, why? How do we resolve these apparent contradictions and paradoxes? So, one answer to the Fermi paradox is the idea that we don't seem to see anyone, is that no one ever evolved, right? So life didn't get complex. Why might we think that? Well, what did we need to produce our civilization on this planet? Well, on this planet, one thing we needed was time. We have good evidence that life was present on this planet 3.8 billion years ago, perhaps even earlier. The planet is 412 billion years old. So we know as a matter of fact, as an observation on this planet, that life was present 3.8 billion years ago. But it took 3.8 billion years, give or take a few tens of thousands of years, to go from the origin of life to a civilization. Let's say from cell to civilization 4 billion years. That's 1/3 of the age of the universe. So a possible answer to the Fermi paradox, the question of why there are no civilizations, is because the Earth is pretty much unique in the Milky Way galaxy, in that it was stable enough, the climate, the conditions on Earth were stable enough for long enough for life to go from cell to civilization. You think about it, that's a big ask. What I'm saying is on this planet, an unbroken chain of life existed for almost 4 billion years, notwithstanding the fact that we live in a violent universe. The sun must have been stable enough for long enough. We know the output of the sun has changed over those billions of years, but it's not changed so radically that it managed to destroy life on Earth. We know that we live in a violent universe. We know there are supernova explosions all over the place. It turns out that there have been no stars massive enough to explode as a supernova in a way that would damage life on Earth or erase life on Earth in this vicinity for 4 billion years. We know that nothing has happened, we know that there have been impacts on the Earth, right? We know the famous impact that wipes out the large dinosaurs. There's been no impact big enough to destroy the unbroken chain or break the unbroken chain of life for 4 billion years. So maybe it's the case that whilst there are billions of planets which may have liquid water on the surface, may have oceans that can support life, it may be that none of those planets in the Milky Way galaxy have been stable enough for long enough to produce a civilization. So that would be a property of the planet itself, the so-called rare Earth hypothesis. Actually, I should say it's a property of a solar system. It's not really just a property of the planet, it's a property of the parent star. You could ask the question, well, if it was a binary system, for example, a binary star system, many stars are binary star systems. Is it possible to have a planet with a stable climate, stable enough orbit in a binary star system to support an unbroken chain of life of 4 billion years? Perhaps not. When we talk about rare Earth, I think I would like to talk about rare solar system. Another possibility with the Fermi Paradox is that it's not a paradox, they are here. So there are intelligent civilizations out there, and they are present in the solar system. It's possible, let's think for example what such an intelligence might look like. Well, who knows, they could have sent nanomachines to our solar system. There could be probes all over the place in the solar system, but they're the size of an iPhone. Then we'd have no way of detecting them. So it could be the technology of a sufficiently advanced alien species, a civilization, is so beyond anything we can comprehend or detect that we haven't seen it. And we've been fooled into thinking that there are no advanced civilizations in the galaxy. And that's certainly entirely possible. Another possibility, another possible resolution to the Fermi Paradox is just that the galaxy is so big, the distances between stars are so great that if you imagine there's another civilization, let's say on the other side of our galaxy, let's say 20 million, 30 million, 40 million light years away, even if they had the most powerful radio transmitters you could imagine, or even if they'd spread out to neighboring solar systems, then it may just be that the distances are so great that the signals are diluted, that we can't detect them because they're too weak, or that it's just very, very, very difficult in an engineering sense to build interstellar spacecraft. Now perhaps you can build a spacecraft that can hop a few light years away to the nearby solar system, 4 light years in our case to Alpha Centauri, but you can't build spacecraft that can traverse a galaxy. Yeah, it's a remarkable instrument. I mean, you think of the predecessor, which is the Hubble Space Telescope. I think it's almost impossible to imagine a world without that. Even if you don't know the images that we're familiar with of the universe, many of them, the spectacular galaxies and star-forming regions, they're from Hubble, but the Webb is a significant step forward. And technically, one of the most important things is it can see what we call longer wavelength light or infrared light. And that's important because if you think about, we want to see the first galaxies forming, so we want to understand how the first stars and galaxies formed in the universe. And so what you do is you look far out into the universe. And because light travels quite slowly across cosmic distances, let's say you have a galaxy that's the most distant one you can see with the naked eye is about 2 million light years away. So that means that the light has been traveling for 2 million years to reach us. And it's a remarkable thing actually to think when you look, it's called the Andromeda Galaxy. And if you know where you're looking, you can just catch it out of the corner of your eye. If you think about it, you're seeing that as it was 2 million years ago. It's remarkable. I mean, it began its journey before we had evolved on Earth. So, in the time it took, and that's the nearest neighboring galaxy, the Webb looks so far out that it's capturing light that's been traveling for over 13 billion years. But the universe has been expanding, and so the light has been stretching. And so, for the most distant galaxies, we're looking back in time almost to the Big Bang. Then that the Hubble was not sensitive to that light, so that the Webb can see the formation of the first galaxies. It's essentially looking all the way back to very close to the beginning of time. And that's very important because we're not entirely sure exactly how those first galaxies form. Well, we almost can. It's not the Webb telescope. There's something called the cosmic microwave background radiation, which is light that was emitted in the universe, and it's a very precise number. It's 380,000 years after the Big Bang, which is not very long at all. The universe is 13.8 billion years old, so we can see that it's microwaves because it's been stretched so much by the expansion of the universe. Going back, that the problem with light is that in those earliest times the universe was so hot and so dense that light couldn't travel through it, so it was opaque. So you can't use light to go back earlier than that, but what we can potentially do, not yet, we're not good enough yet, but the technology we use to now to detect colliding black holes, which is another remarkable thing, but I'll leave that one aside for now. But we have the technology to do that, and that technology possibly could allow us to probe right back to this thing, the Big Bang. And again, whether or not that's the origin of time, we can talk about as well. Well, so this again, I think there's in cosmology, I say this in the show as well, it's one of the most challenging subjects because at one level it makes us feel very, very small and insignificant, and it's true, physically, I mean, the Earth is one planet around one star amongst 400 billion stars in one galaxy amongst 2 trillion galaxies in the part of the universe we can see. I think it's right to say that Einstein really felt, I think that initially that an eternal universe was more natural, but it is also true to say that his theory, general relativity, really doesn't quite rule that out, but it's strongly suggestive of there being a beginning and or an end. And so the theory itself, historically speaking, strongly suggests that, and so he changed his mind, and then we saw the universe was expanding, we observed that, and then we've now seen the oldest light in the universe, the cosmic microwave background radiation, which is the afterglow of the Big Bang. So we know that the universe was hot and dense 13.8 billion years ago. We have so much evidence for that, not least that we have a photograph of it 380,000 years after the Big Bang. It's called the cosmic microwave background. Let's see that. Let me see. We have images of that. That's from the satellite called Planck, a European satellite, and also satellite called Kobe. So we have this images of the afterglow of the Big Bang. We also have theories that tell us about the abundance of chemical elements in the universe which match this perfectly. So there's multiple lines of evidence that tell us the universe was hot and dense, but none of that tells us that that was the beginning. That I think that would be widely accepted that it's a beginning in Einstein's theory. If you just take general relativity, there's a singularity there at the beginning of time. We don't know what it is, but it's there. But it absolutely is true to say that we think that's not complete as a picture, right? So our universe is accelerating in its expansion at the moment, which is one of the great mysteries that was discovered in the 1990s by a friend of mine, actually, Brian Schmidt, got the Nobel Prize for this discovery. He told me once, I don't know if I told you the story before, but he told me that me made this measurement, and it wasn't really, he was looking at supernova explosions, and he'd seen that the suggestion in the data was that the universe is accelerating in its expansion, not slowing down, but speeding up in its rate of expansion, and no one was expecting it. So he thought it was just wrong. He thought, but he couldn't find anything wrong with his data, so he published it and thought, well, that's the end of my career. Oh boy. He was quite young. I think he might have even been a postdoc and he just published it. He thought that's a good scientist, right? I don't think this is right, but I can't see anything wrong with it. I'll publish it. Someone else will tell me where my mistake was. And there was no mistake. And he won the Nobel Prize. Wow. For that discovery. That's the 1990s. So this idea, the universe is accelerating in expansion. The way that it does that is really important. Is it going to carry on doing that? Is whatever's driving that expansion going to change in some way which could actually recollapse the universe again? We give it a name, by the way, dark energy, this thing, but we don't know what it is. I think it's very fair to say, but it looks a bit like inflation, but it's way slower. So maybe they're linked, maybe it's the same kind of thing, we don't really know. And so it's one of the great mysteries. So, but the universe, it looks like the universe is going to continue to expand forever and to continue to accelerate. Yeah, dark matter's in some sense marginally less confusing in the sense that at least we have an idea of what it might be, whereas dark energy, there are people listening to, there are people working on it. So there are theories about what it might be, but I think it feels less explicable given what we know than dark matter. But we haven't discovered what we think dark matter might be, some kind of particle that has got certain properties and doesn't interact very strongly. It's like interacts like neutrinos basically that you mentioned earlier. so really doesn't interact very strongly. But we thought we might have seen those particles, we're looking for them, they would be passing through this room now. And so we could build a detector in here, and we do that, and we look for these particles. We haven't seen them. We thought we might make them at the Large Hadron Collider at CERN. I think many people thought that we'd see the signature of these things, and we haven't done. So it could be that we're not right. About 70% dark energy and the rest, so 25% dark matter. So we're just less than 5% of this. That's crazy. And stuff we can see. So everything we can see in the sky, all the gas and the dust and the galaxies and the stars and the black holes, all those things less than 5%. As according to the standard model of cosmology, and so the other 95%, it's just like who else knows something else. Yeah. And so, but those are models. I mean, it's important to say that it's interesting because so we have a hypothesis which is strongly supported by lots of bits of evidence that dark matter is some kind of particle. So that's what you'll find in the textbooks, but it's true that until you find it, until you see it, then you haven't shown it to be correct. There are, and they're not compelling. No, they all have problems, and most of them have problems with that pattern, the CMV, the cosmic microwave background that we just saw, because that pattern, what you're looking at actually in that pattern is acoustic. It's waves, sound waves essentially, in the early universe that go through the plasma of the early universe. And then they go out, and we know what speed they go through that plasma. So it's almost like you're looking at a pond and you're throwing stones into the pond, and they all land in the pond at the same time and send ripples out, little circular ripples in the pond, and they all overlap. And that's what that pattern is. So we're looking at sound waves going through this plasma, and in those dosaries require the dark matter. The dark matter fits well if it's in there in this plasma, in this kind of soup, this subatomic particle soup that's the early universe, and the way the sound waves go through it fit that idea. So that's one thing. But the idea also came from looking at galaxies and how they rotate, and galaxies and how they bend light and deform space and time, and how they interact together. So there's loads of different bits of information, observations of the universe from the cosmic microwave background all the way through to galaxies and the formation of galaxies, and the theories that we have there that suggest there are these particles around that interact very weakly with light. So they don't really interact with light at all, which is why we don't see them, which is why they're dark. That's just like a neutrino, right? So like heavy neutrinos on, and actually there was a theory once that maybe they were heavy neutrinos, but that's kind of disfavored now. And so we have loads of kind of different bits that fit. This is how you do science. You start with a theory and you make a load of observations, and you can infer things, and you get a consistent picture. But very importantly, until you find it, until you really find that particle, then you don't know, right? So that's what we don't know. Just what we don't know is so fascinating. Just that aspect of it, that 95% of the universe is like, we're not really sure what it is. Yeah, and we've inferred it. So you might say, how do you know it's there? Which is a good question, right? I mean, if we've not detected this stuff, how do you know? And it's from Einstein's theory, really. So it's from gravity. It's from looking at the way that galaxies rotate, and the way that these sound waves moves through the early universe, and the way that the universe expands, because the way the universe expands is related to the stuff that's in the universe. So we can weigh the universe by and find out what kind of different things are in there by looking at the way it's expanded and how that expansion history has changed over time. So it's all what you do with science, which is why it's true that you can criticize any one bit of it, and people will. So online, you'll see in the comments under this, there'll be people saying, but what about this? What about this? What about sure? And it's true that you can pluck away and pick away at any piece of it. But the way it tends to work is when you have this kind of consensus view of something is because you have multiple observations that all fit a particular hypothesis. And by changing one of them, by changing the explanation of one of them, you tend to mess the whole other thing up. You mess the wider description of multiple phenomena up. You mess it all up. So it's quite hard to find the other theories at the moment that will fit all of those different observations. I mean, another example would be the age of things. Is it you? It's interesting that you can look at, we can measure the age of the Earth, right? And you measure it from geological processes, radioactive dating, and so on, and you can kind of measure the age of the Earth. You can measure the age of the sun in a different way. You can measure it by looking at called helioismology, So you can measure how much helium is in the core of the sun, and the sun shines by making helium from hydrogen. So by measuring the amount of helium in the core by looking at basically sound waves, it's like an earthquake that sun quakes. You can measure how much helium's in there, so you can get an estimate of the age of the sun, and then you can get an estimate of the age of the universe by measuring how it's expanding and using Einstein's theory.